Hi all. I was going to do a review on rotation and centripetal acceleration and all these good things. And assuming you guys are okay with work and energy, we did several problems in the classroom, and I also gave you a class sheet. So um, I'm gonna indicate the problems. If you guys can't do it or something is crazy, just try to catch me tomorrow in the tutoring center, and then let's go from there. So basic equations with rotation. At this moment, the rotation is done without acceleration, right? Like imagine a disk that is rotating and it's not increasing its speed as it goes, which means that what happened? So if you take the angle, in fact, let's put it this way. So you have a disk rotating around this point here, and you have a little object like a coin on top of the disk. So the coins go like that, right? So and the coin goes all around and then back to this point. We call period, the time it takes the coin to complete one revolution. So which is pretty much time. And all angles should be given in radians. So an angle that is equivalent to an entire rotation is 2 pi radians, 2 times 3.1415. So um, angular velocity, omega, angular velocity, is equal to the amount of angle some object goes around over time. Okay, and omega relates to the linear speed of that coin. So the linear speed of that coin. So the speed that coin has. Imagine the coin has an odometer, a speedometer, I mean, that measures the speed. So the speed is equal omega r, omega r. So this you should know, and you should know this. Okay, so let's take a look at this problem. What is the period of rotation of Earth? So we want to find t, right, in seconds. Well, Earth goes around in about 24 hours. So we want to convert 24 hours in seconds. So how do we do that? We know that 60 minutes is equal to, I'm sorry, eliminate that. So we know that 1 hour is equivalent to 60 minutes, and 1 minute is equivalent to 60 seconds. So to convert that to seconds, you take 24 hours. So I have hours, right? I want to get rid of hours, but without making any change, I have to multiply that by 60 minutes. And now I have the time in minutes, but I don't want in minutes, I want in seconds. So I can then divide this by minutes by multiplying by seconds, so I'm not altering the quantity. Simplify, and that is 24 times 60 times 60 seconds. Now, what is the angular velocity of Earth? So we want to find omega, right? So what is the angular velocity of Earth? Well, the angular velocity omega, is the angle that takes to complete one revolution, which is 2 pi radians, divided by the period of one rotation. What's the period? We just calculated, right? 24 times 60 seconds. And that's what it is. So you take this number, multiply by 3.1415, divided by all this big number here, and you have a very small omega. Given that Earth has a radius 6.410 to the 6, what is the linear velocity at Earth's surface? So we want to find v. So what is v? V is omega r. So what do we do then? V is equal to pi over 24 times 60 times the radius. And the radius is this big number here. 60.4 times t to the 6 meters. And then you calculate and you have the velocity. So in lacrosse, a ball is thrown. So lacrosse has a stick like this and has a little cup. I don't know if you saw that. And then you put the ball right here. And the players hold right there and then swing this so that, and then let it go, and then the ball just go. Okay. It's kind of a violent game, I would say. That's why the kids, they all use paddings. So in lacrosse, a ball is thrown from a net on the end of a stick by rotating the stick and forearms about you have the forearm too about the elbow. So let's say you have a elbow and the forearm. Okay. If the angular velocity of the ball, angular velocity, you guys should be able to read and understand what those quantities are. So if you get confused of what angle is, angular velocity, and so on, then you get all confused, because I'm not going to give necessarily in problems omega is equal, and then you go to your formula sheet and say, okay, omega is equal theta divided by, no, you have to be able to understand what these quantities are. So angular velocity is omega, and then this is a given quantity, 30 radians per second, and the ball is 1.30 meters from the elbow joint. So this is pretty much 1.30 meters. So what is the velocity of the ball? Velocity equal omega r. So you take the 30 multiplied by radians per second, multiplied by the radius, 1.30, and then you're going to have a number in meters per second. That's the velocity of the ball that leaves that thing. A fairground ride spin. Oh, by the way, if I were to ask you, what is the centripetal acceleration, right? I could ask. So centripetal acceleration, since there is rotation, look at that. There is a acceleration which is always pointed from the object to the center of rotation, in this case the elbow, and the centripetal acceleration is given by the expression v squared over r. So since you calculate the velocity, you just square this number. Where is it? You square this number and divide it by 1.30. And then you have a measurement for your centripetal acceleration. Okay, a fairground ride spins its occupants inside a flying saucer-shaped container if the horizontal surface path the riders follow has a radius. So the radius will have something like this, right? So the radius are right there. So the radius is 8 meters. How many revolutions? So how many rotations per minute? Now, rotations per minute. Revolution per minute. Sometimes is rev per minute. This is units of omega, angular velocity. Will the riders be subjected to a centripetal acceleration, whose magnitude is 1.5 times g? So the centripetal acceleration is 1.5 times 9.8. So we have a number here, right, in meters per square second. So we want to find how many revolutions per minute will the rider be subjected to a centripetal acceleration whose magnitude is that. So we want to find omega. We have the radius, right? So centripetal acceleration is v squared over r, correct? But v, it's another way to write centripetal acceleration, is equal omega r. So I'm taking v and replace by omega r. So you can also write, so we can simplify this, centripetal acceleration as the product of omega squared times r. So we can then calculate omega as being square root of centripetal acceleration over r. What I did, I divided both sides of the equation by r, right? And then I can, in a square, I took the square root, and then I have my omega. So this is going to be given in radians per second. And I have to convert that to revolutions per minute, okay? So how do we do that? Well, 2 pi radians is equivalent to 1 revolution. So, radians, 1 radian is 1 revolution divided by 2 pi. And that's, so what do? I take my omega, which I calculated here, right? Whatever number this is, I, instead of write in units of radians per second, I will write in units of 1 revolution per second, all of that divided by 2 pi. So we take this number divided by 2 pi, and that is our omega. Riders in an amusement park shaped like a Viking ship hung from a large pivot, are rotated back and forth like a rigid pendulum. Sometimes near the middle of the ride, the ship is momentarily motionless at the top of its circular arc. The ship then swings down under the influence of gravity. I think I saw that. It stays like this. And everybody screams when he's there. He keeps swinging, right? So he keep going like this. And then swing, swing. And every time kind of go a little bit further, and then get to a point that thing rotates. And then you have pretty much a full rotation going on, and it stops right there sometimes. I think I remember that. Okay, assume negligible friction, find the speed of the riders at the bottom of its arc, given that the system's center of mass travels in an arc having a radius 14 meters. So R is 14 meters. And the riders are near the center of mass. So they are just saying, hey, consider everything to be a point. And what is the velocity at the bottom part? Okay, so how can we think about this? Well, you can use the concepts we learned this in this chapter, but also since we are learning now conservation of energy, we could use conservation of energy for that. See, friction is negligible. So basically you have this thing going down, and we want to find the speed up here. This is your situation A, this is your situation B. So you do your energy conservation table, A and B. Does it have kinetic energy at point A? No, momentarily motionless at the top. Kinetic energy is 0. At a point B, you do have kinetic energy, half mvb squared. How about gravitational potential energy? We do have mg to r, right? The distance from A to B is 2r, r and r. And then the P, point P, is the one that gravitational potential energy is 0. So you add these two quantities now, mg to r is equal half mvb squared, right? And then we can find the speed at the bottom part, that's part A. What is the centripetal acceleration at the bottom? Well, centripetal acceleration, go to the equation, is VB squared divided by R. So you take the VB, we just calculate, divided by R, and get it done. Draw a free body diagram of forces acting on a rider at the bottom. Okay, at the bottom. Free body diagram on the riders. So the riders are sitting on a seat, right? So they do have weight, their own weight, and they do have the normal force the seat is exerting on them. So that's the free body diagram. Find the force exerted by the rider on by the ride on a 60 kilograms rider and compare to its weight. So we want to find the force Fn. So what is the definition of centripetal force? Centripetal force is the net force, the resultant force in the direction of rotation. So at the bottom, the lowest point in that pendulum, the direction of rotation is the center from where the pendulum starts, right? So you have a pendulum like this, right? So the net is Fn minus Fg, which is the weight, and this is equal to your centripetal force. Centripetal force is the mass times the centripetal acceleration. So we have this, we have this, we have this, we can find Fn. This, and then pretty much that's it, okay? Calculate the centripetal force on the end of 100 meters when the turbine blade that is rotating, what is this? You have to interpret that as omega, revolutions per second. But when you operate omega and relate that to speed and time and all of that, do not use revolution. You have to use radians. So one revolution, you want to cancel revolution. How do we do that without altering this resulting ratio? We have to multiply by 2 pi radians. One revolution is 2 pi radians, all of that per second. So our omega, to begin with, is 0.5 times 2 pi radians per second. What we want to find? We want to find centripetal force. Centripetal force is mv squared over r. So at the end of a blade, so the blade is right here, the centripetal force is equal is rotating. I think it's supposed to be assumed this is a point mass, I guess. And then, so the mass is given, but we don't have the velocity, we have the radius. But see, V is equal omega, and we did that before, right? Omega r. So you can write centripetal acceleration as m omega squared times r. Since see, one of these r's, r squared, will cancel with this r in the denominator, you're going to have that. So now we can solve the problem. We have the mass, we have the omega, it's right here, and we have the radius. And then we can find the centripetal force. Calculate centripetal force on the end of a... Oh, I just did this one. Okay. Okay. Let me know if you think it's okay or not.